Good afternoon, and welcome to today's plenary session. It is our pleasure to introduce our speaker, Dr. Corinne Quéré. Dr. Quéré is a Royal Society Research Professor of Climate Change Science at the University of East Anglia, UK. She conducts research on the interactions between climate change and the carbon cycle, including those mediated by marine ecosystems. She also conducted research at the Max Planck Institute for Biogeochemistry in Germany and the British Antarctic Survey. She instigated and led for 13 years the annual update of the global carbon budget within the Global Carbon Project. She was author of 3 assessment reports by the Intergovernmental Panel on Climate Change and is former director of the Tyndall Center for Climate Change Research. She chairs France's High Council on Climate and is a member of the UK Climate Change Committee. These are 2 independent committees that advise their respective governments on how to respond to climate change. It is our pleasure to welcome Dr. Quéré. Thank you.
Thank you very much. I'm really thrilled to be here in such good company. I was actually sitting in the wrong registration queue at 7 a.m. this morning, and then I heard somebody say, Governor, Governor, here, this way. And I thought, great foresight from the organization committee. What a way to widen the policy-science interface. We know already a lot on how the Earth system operates, thanks to the people sitting in this room. This is illustrated by this incredibly powerful figure published by, in the 6th assessment report of the Intergovernmental Panel on Climate Change, the IPCC. So this figure shows current estimates of the changes in the concentration of CO2 in the atmosphere at the top, and estimates of the global temperature change compared to today at the bottom. And it goes from the deep past to the next 300 years. The figure combines, obviously, different types of estimates based on proxy data. Several conclusions, very powerful conclusions, can be drawn from this figure and the underlying science, starting from the pre-industrial time here today, moving back in time. The glacial periods of the past million years demonstrate that the natural carbon cycle was distributed rather differently in the past. When carbon storage in the ocean increased from a combination of temperature, circulation, and changes in marine ecosystem productivity, while carbon storage in the terrestrial biosphere diminished from a combination of reduced forest area and reduced vegetation density generally. Those changes are substantial, reducing atmospheric CO2 concentration by 100 ppm and amplifying the glacial cycle, which itself reached 4 degrees Celsius warming. The last glacial cycle is also a proxy because of this little bit here. It's also a proxy for what happens in the natural environment if planetary warming approaches 2 degrees Celsius of warming, which is approximately 1 to 2 degrees the warming observed at the last interglacial period. And this evidence was key to the warming level committed in the Paris Accord, which aims to limit climate change in the future well below 2 degrees and pursue efforts to limit climate change to 1.5 degrees. And that's because of that bit of evidence here that these thresholds are there. Moving back in time further now, the covariations between atmospheric CO2 and temperature have been a signature of the Earth's climate over tens of millions of years. It also shows extreme events have occurred in the past, such as during the Paleocene-Eocene thermal maximum 56 million years ago, where a rise in atmospheric CO2 in the area of 1,000 parts per million co-varied with warming of at least 10 degrees Celsius today. These events undoubtedly show the substantial perturbation of the carbon cycle. That substantial perturbation of the carbon cycle can take place when the Earth's climate changes. Although the processes that cause these changes, those in the deep past, are not the same as the one that causes the change in the future, at least in the short term, the evidence of a living Earth is stunning and should be taken very seriously. Going forward in time, in the next century and beyond, the trigger of the 1.2 degrees Celsius warming, of planetary warming that we've seen so far in the past century is undoubtedly emissions of greenhouse gases from human activities, particularly CO2. This has been demonstrated through physical understanding of the processes, the rapidity and change and patterns of the warming compared to natural variability, and the former attribution in climate models force with natural and anthropogenic factors. The three big questions going forward are, in my view, what is, starting from the right-hand side, what is, in fact, the future of global CO2 emissions so that we can start to project warming in a bit of a more precise way? How large are the feedbacks between the carbon and climate change that will amplify warming, and are there surprises in the pipeline? I will touch on some elements of these three questions today. Starting with the first, what is the future of global emissions? The IPCC has explored a wide range of future CO2 concentration pathway extended to year 2300, which you see here. Scenarios go from a stringent mitigation scenario in blue here, limiting warming well below 2 degrees Celsius, so 1.8 degrees Celsius is the warming stabilization level of the bottom scenario here, to a very high emission scenario, the SSP5, at the top here, that sees 4.4 degrees Celsius of warming already in 2100, continuing to warm afterwards, which is the red scenario here. The spread in emissions, in my view, as I will demonstrate in a minute, is too large, in my opinion, given what we know today about current trends in emissions and their drivers. But before I go into climate policies in the first part of my talk here, what we measure is the concentration of CO2 in the atmosphere. But because CO2 is a long-lived greenhouse gas, stabilizing the concentration implies that the growth rate actually peaks, then reduces and reaches eventually net zero. You see the growth rate here associated with these concentration stabilization pathway. And to a first order, the growth rate corresponds to the emissions of CO2, which are primarily from fossil fuel burning and land use change. And hence, in all cases, CO2 emissions need to peak and be brought down to zero, whatever the level of carbon stabilization we're prepared to accept and whatever the level of warming we're prepared to accept and manage. You see immediately that the bottom scenario, the one that limits climate change well below 2 degrees Celsius, as in the Paris Accord, this scenario is pretty heroic, with the growth rate decreasing abruptly and staying below zero for a while, meaning that we would be actively removing vast amounts of CO2 from the atmosphere. So let's dig in the first part of my presentation here into the realism of the future scenarios before we go into the natural carbon cycle. To limit climate change anywhere near 2 degrees, global emissions need to peak essentially now or in the coming few years and start declining rapidly. So are we approaching peak CO2 emissions? So here are the CO2 emissions pathways since 1990 from burning fossil fuels, the primary cause of climate change. So global emissions for 2023 and including the first half of 2024 revealed that there is so far no sign of decreasing fossil emissions, but global emissions are, on the other hand, not growing as fast as they used to be a decade ago. Emissions have grown in that period, the last decade, about 0.6% per year, still a growth, but that growth was much slower than the 2.8% per year that we had seen in the 2000s. The slowdown in the growth has been attributed to more than 3,000 climate and energy policy work worldwide. The policy attribution has been looked at in detail, including by myself, by scrutinizing commonalities among countries where emissions decrease. So what you see here, each little stamp is the relative change in global fossil CO2 emissions by country. You see that there are 18 countries there. There are countries where the emissions decrease for at least one decade, both in territorial basis and consumption basis, in the presence of growing economies. These countries include the US, many European countries, including the UK and France. And recently, after this study was published, that group was joined by Japan, Brazil, and South Africa, and the group is widening. A close look at the drivers among these countries show commonalities. So countries that succeed in decreasing their emissions are countries that use less energy, either because they're becoming more energy efficient or because their economy relies less on energy sources. There are countries also where renewables replace fossil energy. This is critically important because to reduce emissions, you have, of course, to remove the sources of fossil energy. Countries where the renewable energy grew in parallel to fossil energy, such as many emergent economies, but also countries like Canada, did not, in fact, decrease their emissions substantially. Very important point. And the last point was these countries that are there have a lot of climate and energy policies. And in fact, the more climate and energy policies were in place, the more the emissions decrease. This later point, the policy attribution was confirmed separately by colleagues that have, in fact, quantified the avoided emission and shown that, in fact, climate policies work, they succeed, and they explain the change in the growth in emissions between the two decades. Therefore, national climate policies work, but we need more of them to tackle climate change. I insist on this here because I hear a lot of scientists saying nothing is happening about climate change, and I don't want to hear this anymore. Actually, a lot of things are happening about climate change. We just need to have more of those things faster and at larger scale. I've talked about fossil emissions, but there's also, of course, land use emissions. Although in size, they're much less than fossil emissions, they are needed to achieve what we need to tackle, to stabilize the temperature, which is net zero emissions. Thinking that there are emissions, for example, aviation or agriculture, that we cannot bring down to absolute zero, and we have to offset with sinks. Now, what is the status of the land use emissions? So the trends in the permanent deforestation, which are in dark orange here, slight decrease, but still much larger than permanent forestry growth from afforestation and deforestation, while the emissions from forest management from shifting cultivation is about equal to the regrowth from, again, forest management. If you add those curves up, you see a slight decline in those net emissions with large uncertainties, only a gentle decline, not quite enough to offset the growth in fossil emissions, so that in conclusion, we're still a long way from net zero CO2 emission, even though there has been huge progress in climate policy. Deliberate carbon dioxide removal that we can do by managing we can do with active technology such as BECCS, so bioenergy with carbon capture and storage, and DACS, direct air capture with capture and storage. These technologies at the moment, have a minuscule amount of offset of emissions. You see the number here coming from the Global Carbon Budget Annual Update. These technologies are going to be next to essential in a few decades' time to complement the terrestrial carbon sink that we can achieve by afforestation and reforestation. The science and implementation needs of these technology needs to move a lot faster. There are big questions out there, including to identify the storages where the capacity for these technologies is needed, to estimate and assess the risks and limitation, to build the infrastructure from the storage to the locations where they are needed. If I now put all the emissions together and line them up with future projections over this century, this is an updated figure from, again, the last IPCC report, we see that despite significant recent progress in tackling climate change, global warming levels under current policies, which is the red area there, is still close to 3 degrees warming, with a realistic range starting well above 2 degrees, 2.2 here according to this estimate, with a higher limit around 3.5 degrees. The scenarios most studied, the SSP 8.5, which I showed in my first slide, is actually well above here, so that the scenario is no longer realistic. However, the Paris Accord commitment to limit climate change well below 2 degrees in the green there, or even the red there, is not yet within reach at all. It would require both additional commitments, so current commitments are here in the little interface here. It would require both additional commitment and additional policies, particularly in the short term. Both these scenarios, so the current, especially if it's going to be on the high-hand side, and the bottom one, have very big implications for the carbon cycle, which I will go in a minute. Let me move to the second question, which is how large are the carbon-climate feedback, given what we know about trend in CO2 emissions. So I'm pleased to say, as I just said, avoid the trends. I think we have avoided those trends. Those of you who are my age, you will know that this scenario was actually plausible still a decade ago. I think it's no longer the case, but we're not on the bottom line scenario over here. To come to the SSP 370, the one that is just there, one would still, that is still a scenario that is very high, would still have to massively reverse global climate policy and reverse or offset gains made by technological developments in the low carbon economy, electricity generation, particularly wind and solar panel and power and also storage. Temperature that match current commitments range between 2.2 and 3.5 degrees. Yes. So let me move on here to the feedbacks. So emissions of CO2 take place on top of a very active carbon cycle. A little warning here that I'm switching units now to carbon units that are used in science, while I was using CO2 units before used in policy. There are several reservoirs of carbon that can be mobilized on decades to century timescales, including carbon in the terrestrial vegetation and soil, which stores 4 times more carbon than the atmosphere today, and carbon in the ocean, which stores 50 times more carbon than in the atmosphere today. The natural fluxes in thin lines here can be a lot larger than the anthropogenic fluxes in thick lines here. So these are, orange is the fossil fuel emissions for the last decade, green is the land use emissions over the last decade. But the natural fluxes are thought to be in equilibrium over multiple years. The reservoirs themselves respond to the increase, the buildup of CO2 in the atmosphere. In the ocean, this is mainly a physical chemical response, dissolved CO2, then chemical reaction, then transport by physics, and on land, primarily a CO2 fertilization of photosynthesis and increased water use efficiency. The land and ocean combined absorb more than half, 55% on average, of the emissions, of the annual emissions, considerably slowing down climate change. We know these numbers based on combination estimates that use energy and land use statistics for the emissions, PCO2 and other observations for the ocean sinks, complemented by models, and models only for the land. Therefore, it's a good test of the validity of the existing estimates that can be done by checking if they add up. If we had perfect data and perfect understanding, then the sum of the emissions, which is at the top, fossil and land use, this is time now on the x-axis, would exactly equal every year the sum of the ocean land sink plus atmosphere, which is at the bottom. So the red dotted line here is the reflection of the full red line at the top. And you see that, in fact, despite the uncertainties in the various estimates, the combined estimates, in fact, add up and are consistent. They are consistent both in the mean, where there is actually barely any lag. There is a little bit of a lag here in the sum of the mean, but it's really quite small compared to the uncertainty. And also, there is a good match of the trend over the time period itself. Although this is not a proof that all the estimates are good, it is a necessary condition to, and it does suggest that the first order understanding is reasonably sound. On the other hand, if you focus on the things that are not explained, so the difference between the two curves, the emissions do not match exactly the sink, and the mismatch, which we call the carbon budget imbalance, is extremely instructive to identify the limit of our collective understanding. Because of the structure of the mismatch, we think that this comes from some inadequate representation of the response to climate variability of the land and or the ocean sink. This mismatch has not decreased in the past 12 publications of the Global Carbon Budget Annual Update, suggesting that the way that we assess the carbon budget today has intrinsic limitations in our capacity to represent that change, and we could move forward with different methodologies. Focusing for now on what we do know, the land and ocean sinks can be split between their response to changing atmospheric CO2 and their response to changing climate change and variability. The response to rising atmospheric CO2 is positive everywhere, so that when CO2 increases in the atmosphere everywhere, the land and ocean sink increase. So this is the top panel here. The response to climate change is much more variable and much more interesting. It's predominantly positive, meaning more sink in the boreal forest due to its northern expansion, and predominantly negative in the tropical land due to the response to climate conditions, particularly warming and drying. Over the ocean, surface warming can simply account for most of the modal change. These are attribution done with models. Overall, the carbon climate feedbacks estimated here reduce the sinks by 20% for land and 7% for the ocean in the past decade. So the climate carbon feedbacks, we think, are already active today, reducing the efficiency of the sinks. The trend attributed over recent decades are unsurprisingly perhaps similar to the trends projected this century, which I show here as reported by the IPCC. The response of the atmospheric concentration, showing here this negative feedback dampening climate change for the land and ocean, is very similar to what we could infer in the past decade. And likewise, the response to climate conditions, to changing climate conditions, show a positive feedback that is there that reduces the sinks by an estimated 30 to 40% approximately. The effect of permafrost has been talked about a lot. There are several estimates, independent estimates, 20 or so, that have been assessed by the IPCC. And despite the very broad uncertainty, their effect is here, is the pale brown effect that you see over there. Unlikely to be large this century, with even the largest estimates producing moderate feedback, I insist, this century. The response of the ocean is also predominantly a warming effect, and I will go into this in a minute. Beyond 2100, now this is where things become interesting, but also where we have much less information. The land and ocean CO2 sinks could transition from being sinks to sources of carbon, either under very high emission scenario or under very high stringent mitigation response, so low emission scenario. On the high end, the response is mostly for the land, not for the ocean here, an outgas of some of its carbon sink because of climate change conditions post-2100 in the next century, the century after that, according to IPCC models, which consistently show that the land biosphere starts to outgas at some point in time. On the low end is simply because the sinks actually that responded to the growing CO2 growth rate in the atmosphere would respond the same way if the growth rate in fact starts to decreasing actively, so that deliberate CDR, for example, if we were so successful that we can do them on the tens of billions of tons basis, then would have to consider the fact that the land and ocean sink would potentially start outgassing their carbon, particularly on land. I now want to dig a little bit deeper in two components of the feedbacks. So I focus until now to things that we know well established in the IPCC and everything. So I've selected two components of things that I've looked at together with collaborators, one in the ocean and one very briefly on land. The Southern Ocean, extremely interesting region, one of the most active environment, most important regions regulating the carbon storage in the ocean in the modern times, but also in the past. It's also one of the most uncertain regions, where model spread, whatever, regardless what you look at, is the largest in pretty much any metric, be them physical or biogeochemical. The Southern Ocean today is not only undergoing changes from global warming from greenhouse gases, but also from the influence of stratospheric ozone depletion, which we had in the 70s until the Montreal Protocol in the 1990s. In the study that I will show here, led by Teresa Jarnikova, we have conducted 6 model simulation looking at projections using the UK Earth System model that simulates changes in the atmosphere, ocean, and carbon cycle interactively using a low and a high emission scenario, the two that you see there, and 3 ozone scenarios. When thinking about carbon storage in the ocean, in the Southern Ocean, changes in wind conditions are critical. Those of you who have worked on glacial conditions, you will know that, because they largely determine the exchange of water between the surface and the deep ocean. The combination of scenarios that we performed allowed us to assess independently the contribution of ozone and greenhouse gas. Both ozone, so you see the changes in wind in the on the left-hand side, total. Both the ozone depletion and global warming tend to increase wind intensity. They do it in different seasons. But as ozone reverses, then winds also, the effect on wind also reverses. This is what you see on the top-hand side, effect of ozone on wind. Initially, depletion of ozone increases winds by a lot. This is not quite 1 meter per second. And then when ozone recovers, then the wind reverses. The effect of warming is simply scales up on wind, scales up with the emission scenario. So that when you add them up, you have in the past very strong increase in wind, rapid, then leveling off, and then in the future, it depends on the emission scenario. For ocean properties, surface warming in the top panel here is directly related to greenhouse gas emissions, and overturning is directly related to the changes in the winds. However, in the middle here, the mixed layer depth, so changes in mixing condition at the surface, extremely important for the marine carbon cycle, both for ventilation and also for ecosystem productivity, is much more complicated as mixed layer depth first deepens from the ozone effects on winds here initially, and then stratifies from the combined effect of warming and increased precipitation at high latitudes that makes the water less dense. The implications for the carbon uptake depends on the influence of ocean physics on two things. First, on how the ocean is going to retain its natural carbon cycle. Lots of carbon in the ocean, 50 times more than in the atmosphere. That's a thick arrow. But second, how these processes are going to influence the uptake of carbon, the additional carbon, the anthropogenic carbon that we put in the atmosphere. Temperature has the same effect in the same direction, both for natural and anthropogenic, but that's not the case for the mixed layer depth and for the overturning, where an increased overturning brings natural carbon up to the surface and outgasses it. It also increases the uptake of anthropogenic carbon, and these two effects offset each other. So to know what is going to be the net effect into the future, knowing that the IPCC and the last IPCC said that one of the biggest uncertainty that remains is actually what is the effect of the winds going to be in the carbon storage in the Southern Ocean. And you have to calculate it, which we have done here. We calculated the role of each process for the past 50 years and for the future, the last 50 years of this century here. You see, and we have decomposed the effect of temperature, overturning, mixing depth, and ecosystem fluxes, but only those that are regulated by the changes in the nutrient supply, so physics-related ecosystem processes. The first striking result is that ozone effects dominate past changes very clearly in the last few decades, but greenhouse gas effects dominate future changes in the Southern Ocean, although they can still, hence the changes over the past decades cannot serve as a direct proxy for the changes today and the changes in future decades, although they can still serve as a proxy to understand the effects of winds on the carbon cycle. The second striking result is that the direct effect of warming, which you see in the future here in orange, completely dominates other physical processes, mainly because of the opposing influence of mixing processes, so mixing depth and overturning circulation on the natural and carbon cycle component. From these results, if you put those together, we can calculate the strength of the carbon-climate feedback in the Southern Ocean, which we show here with a metric that uses the changes in the surface dissolved inorganic carbon compared to the changes in warming level as a metric. And instead of the conventional sort of wisdom, which is that the climate change, the carbon-climate feedback will grow with a warming climate, with the level of climate, we actually show the contrary for the Southern Ocean, which is with the scenario SSP3 7.0, which goes to 3.5 degree warming at the end of the century. Actually, the carbon-climate feedback decreases because of this compensating effect on natural and anthropogenic carbon, which grows through time. Also, the effect becomes completely dominated by temperature. If you remove temperature effects, no warming effects here, the feedback actually goes essentially to zero, which is very logical as the vertical profile of the IC flattens up essentially. So this is not to say, as I said, the IPCC flagged the uncertainty this century. the wind has been uncertainty the century. We show, in fact, that the effect of wind is small compared to the warming effect, which is, in fact, well known and included in models. So this is, in fact, good news in a sense that it constrains the climate projections even further. This is not to say that big uncertainties remain, of course, in the Southern Ocean, but they have more to do with different things. The representation of the mean ventilation of carbon in models, the response of ecosystems to warming and ocean acidification, which we have seen in the past has been actually very important, and the long-term stabilization level, which we did not address here beyond 2100. Very briefly, I want to talk about disturbances on land, particularly wildfires, which have received, rightfully so, a lot of attention recently. It's well known that climate change increases the hot and dry conditions that promote wildfires, but attributing the role of climate change for wildfires has been difficult because the land is also heavily managed and influenced by human activities. In the study led by Matt Jones, my collaborator at the University of East Anglia, we used machine learning to disentangle the drivers of climate change using 9 different proxy gridded globally for changing climate conditions, including soil moisture and fire, weather index as proxy for climate, lightning flash density as proxy for natural activity, and population density and forest continuity as proxy for human interventions. The data was all gridded, and the machine learning algorithm grouped the regions into 12 what we called forest pyromes, which is what you see at the top here. By doing this, we could isolate the extratropical pyromes, which are red, orange here, over there, as regions that came out as being particularly sensitive to climate conditions. Now, running this over the past 22 years, where we have sufficient observations, the pyrome analysis does show rapidly increased forest burn area in extratropical pyromes that we link to climate change that were partly offset by declining burned area in tropical pyromes. After combining these trends with an estimate of carbon stocks mobilized during forest fires using the GFED model, we estimate a 60% increase in forest fire CO2 emissions globally over the past 22 years, with increased vulnerability of carbon stocks. Matt Jones led the first State of Wildfires report, which you might have seen, it came out last week, and further re-emphasized the importance of fire CO2 emissions anomaly of 2023, particularly in Canada, where they were almost an order of magnitude larger, the emissions, than the long-term average. We produce a lookup application where you can explore these emissions. In the steady state, forest fire emissions get eventually replenished by regrowing forest. However, an increase in forest fire emissions can translate in a delay between emissions and regrowth, leaving more CO2 in the atmosphere and causing a positive feedback amplifying climate change. About half of the Earth system models used by the IPCC include estimates of wildfires, but the models reproduce only poorly historical trends, and therefore projection is low, although the IPCC still stated that the magnitude of that feedback should be, it's a thought, less than what is expected from permafrost. As I concluded for the Southern Ocean, the big questions we have now are shifting from what will happen this century, which has been the focus of the IPCC up to now, to what will happen at stabilization level with processes such as these wildfire emissions coming out of balance beyond this century and in millennia timescale. Going back, in conclusion, to the Earth system through time, to the question, what is the future of global CO2, we can say a lot based on inertia in climate policy. We have avoided the very high emission scenarios above 4 degrees, but thanks to climate policy, but we are not on a path to climate change well below 2 degrees. It is critical to keep track of the evolution of the carbon cycle and climate change, so we can fine-tune this, but it's even more critical that we re-emphasize the importance of ambitious, stable, planned climate and energy action and policy in the long term, and develop the methods and technologies such as BECS and DACs, both in their scientific understanding and also their deployment. To the question, how large are the carbon climate feedbacks, we have greatly narrowed the uncertainty for this century with the sum of amplifying feedback in the area of 30%. Those effects are included in IPCC projections to 2100, not the extreme side of this. And we have reached a time, in fact, we're so advanced in climate change that we can literally look out the window and measure what's happened, and we should, to help constrain the projections. It is time to think about what happens beyond those feedback. For example, we have been good historically about managing some of those feedbacks, including wildfires, and if we can say more about their long-term evolution, we can devise not only mitigation strategy, but also guide adaptation pathways that could include managing some of those feedbacks, including pests and disease outbreaks, disturbances, and wildfires. To the final question, are there surprises in the pipeline? I would say we have explored this question far less. This concerns the century-scale stabilization of atmospheric CO2 not only once the emissions have reached net zero, but also once the natural land and ocean ecosystem reservoirs have reorganized themselves, including how they will and could adapt to new natural conditions, either naturally or helped with climate action. This will be important to assess additional risks and anticipate warming level and its consequences more finely. Surprises include the possibility that extreme response in the carbon cycle take place. The IPCC states there is no evidence of abrupt changes in carbon feedbacks in the coming century, but the jury is out beyond this. This addition is mine. I do look forward to finding out more insights on these questions at the conference this week, and thank you very much for your work and your attention today.